This is a demonstration, part two of our demonstration on linear regression. In this part of the demonstration, we will go over residuals analysis and fit checking for linear regression. So in terms of residuals analysis, anytime you run a linear regression, you can predict residuals. I'm providing on the left-hand side syntax in Stata for how you would predict residuals. You can predict E, which is E is the name of your residual. E, you could write anything you wanted. You could call it resid or residual, but you predict your variable name that is your residual, common residual, to indicate that you want the residuals. We would also want to predict the expected value of the outcome. So I'm calling this y hat, and I would just type predict y hat. Then we evaluate several diagnostic plots. So two diagnostic plots, which are shown here, is a histogram of the errors. The residual errors should be approximately normally distributed, about a mean of 0. And from the histogram, as you can see, they are indeed about approximately normally distributed, and the center of the distribution is at 0. We can also look at a scatter plot of the predicted value of the outcome against residuals. And we do not want to see any sort of a pattern in this scatter plot. We should see random scatter. And for the most part, we do see random scatter in these data. There does not appear to be any discernible pattern at all. Because conditioning on the predictors, the expected value of the outcome should have no relationship with errors. These errors, these residuals should be completely random errors in theory. Next, we can look at a graph of residuals versus our x variables, and however many x variables you have, you should look at that many graphs. So here I'm doing just two examples. I'm scattering age against my residuals, and I see up at the top right, I see a random scatter, and I'm also scattering years of education against the random residuals. And similarly, I see a random scatter here. So this is all looking positive for the fit of this model. An additional analysis to do is what's called a leverage versus residuals plot. The Stata syntax is relatively simple. Just after you run a regression, here this is after the multiple linear regression that I ran as shown in part 1 of this demonstration. You just type into Stata LVR2 plot. And what this shows is on the x-axis are the normalized residuals squared. So higher residuals indicate there's a greater residual. So there's some potentially values with a large deviation from the model fit line. And on the x-axis is leverage. So points with high leverage have a high probability of actually affecting your beta coefficient. So residuals affect your model fit, and leverage is associated with producing, we'll call them biased results. It's possible to have points with high leverage and points with high residuals. You'll want to investigate these points and understand them better, and potentially add some variables to your model, or potentially explore some nonlinear relationships in order to address them. But ultimately, where we really worry is when you have points in the upper right-hand corner of this plot. That means that you have points with high residuals and high leverage, and that indicates a problem with your linear regression. We do not want to see points in the upper right-hand side. Just to illustrate, I'm going to change the data to illustrate a problematic value. As a reminder, as we can see at the graph on the top right-hand corner, the age distribution ranges in this sample ranges from 65 to about 78 years of age. So I'm going to select one random observation, and I'm going to, I want to change the data simply to illustrate a problematic value. And so I'm going to replace age equals 40 if for this one ID. And then I'm going to rerun the regression, and then I'm going to look at my leverage versus residuals plot. And as you can see, I changed this age variable to 40, which is way outside the range of 65 to 78 for age. And you can see clearly there's a point here that has high leverage and high residual. This point alone has the potential to change the beta coefficient or bias the beta coefficient, at least for age, in the association with total cognition, and it has the potential also to mess up other beta coefficients in the model potentially. And so this is common. This is common in research. It may indicate that there's a misentry of data, and so this is a way of telling you that you should go back and look at your data and explore your data and understand where these odd values are coming from. So, as I mentioned in part one of the demonstration, we used this model to explore associations. Is this model also useful for prediction? Well, when we were exploring associations, we were really interested in these individual beta coefficients and understanding what was related to cognitive functioning, and what was outcome and what was not related to cognitive functioning. If we were interested in prediction, which is a perfectly fine use of linear regression, in that case, we would be primarily concerned with the R-squared value up here. Now, the R-squared value is 0.25, which suggests that here, 25% of the variability in the cognitive performance outcome is explained by these covariates. That's still a relatively poor, I would say, prediction, although it depends on what criterion you are looking for. Perhaps you could add additional variables that you know to be related to or predictive of cognitive functioning to improve that prediction. This ends part two of the demonstration on item of linear regression. Thank you for listening.